any the process of natural language processing starts with this document parsing and document word embedding. And uh, so what happens is that if whenever you get some text, what would you do with it? You could develop any kind of applications with it, such as sentiment analyzer or a chat bot, or some text summarization, or a news reader app. So all of this starts with one thing, that you have to understand the process of natural language processing in the and the steps involved in it. And this step of document parsing is the first step in it. Now, when we compare what the steps of natural language processing with the equivalents in a computer language compiler, the tokenizer, which essentially means that you are given a sentence and you have to take out words from it, words or maybe characters. But if you take out characters and build your vocabulary on that, that will lead to huge memory use. And most of the times people are okay with using words. And the corresponding equivalent, if you have studied computer language compiler, then you might be familiar with scanner, like scanner or lexer. So scanner is, it's basically that when you have to compile a code, you have to scan the code and you have to figure out if there are any syntax errors. And the result of tokenizer is that you get a vocabulary, you get words such as a and b or alpha beta gamma. And what we get in computer language compiler is lexicon, which is essentially tokens which are meaningful to the computer. Now in NLP we have parser, in computer language compiler we have compiler. And the whole process is that the outcome of this tokenizer and building a vocabulary and parser is that you get to understand the tokens in it, the terms, the words, the sentence in your natural language text. Now, let's suppose this is a sentence given to us, that Thomas Jefferson began building Monticello at the age of 26. Now, if this sentence is given, we would work on it and keep. I have presented this sentence over here because we're going to be using it in our following slides. Now, this slide talks about one hot vector. Are you familiar with one hot vector? If yes or no, just a brief answer.
No.
Okay, so I'd explain. When you're given a text, let's say I'd open Paint instead of this. Let's say you have a column in which you have values such as A, B, A, B, and then maybe we would say C and then B again. Now, what would happen is that if you want to create a one hot vector from it, you would go this way. How many values do we have? 1, 2, 3. No. We have unique values. 1, 2, and 3. Unique values meaning how the set of all the values present in this column. Now, when we talk about creating a one hot vector from it, we essentially have to create 3 columns for each one of the variables, and we name them A, B, and C. Now when we name them A, B, C, then we start filling them. Do we have A here in this one, in this field? 1 second. I'd also draw horizontal lines so that we don't confuse. Okay, now do we have a here? Yes, we have a here. We would write 1 and 0 in the others. If do we have b a here? No, we don't have a here. Do we have b here? Yes, we have b here. Do we have c? No. Do we have a? Yes. B? No. C? No. B is there, so we put 1 on the 1 for B and 0 for the rest. Similarly for C, we put 1 for C and 0 for the rest. Now what is happening is we call this vector one hot vector because only one value in the entire column is 1 and rest are 0. So this is basically one of the way to encode our incoming text into the form of zeros and ones, or that's how computers understanding. If you're given some text like this and you have to make a computer understand that text, the first step you have to do is convert that natural language text into some kind of numbers that the computer can understand. That because computer in the sense in very high level language is just like a calculator, and it works on numbers, and in the depth it works on zeros and ones and binary language. Now if we is that clear? What is one hot vector representation?
Yes, yes.
Okay, then we come back here. This is some code which is producing the one hot vector representation of the sentence. The sentence is this: Thomas Jefferson began building Monticello at the age of 26. Now, what is happening here is it is trying to build a vocabulary by creating one hot vectors for the words. And the way it does is it has sorted uh, uh, the sentences, sorted the words from the sentence. We have this over here. Now, if we go here and paste it here, then Thomas Jefferson began building Monticello. Now, what words do we have here? Monticello at the age of 26, right? Now, first step to building a one hot vector is that you have to sort the sentences, sort the words in it, and the way it sorts words is numbers comes first, then comes the capital letters J, T, capital T, and then I think okay, so not T. It's after J comes M, and this is how we okay. This is 3, this is 4, and then the small letters, which is pretty straightforward. Age should come next. Age, yeah, right. So and so forth. Okay, and 6, so and so forth. Essentially, it's created this matrix by creating this one hot vector. All of the code is present also on this page. You can refer to it later. And this has been taken from this book. I'd share the book with you on later, and you can go through it. And This was for your understanding that how it creates one hot vectors. Now what is happening is you are preserving the order. If we look at this line, it is saying first word is Thomas and second word is Jefferson. Then next word is begin. It is preserving the order of the words, but it is going to be huge volumes of data if we store our NLP text like this. Now, the way to reduce that problem of overflowing memory and huge amounts of space requirement, we came up with the idea of bag of words vector, which is essentially we are only bothered about the word frequency of the words and not their order. So the next what we are going to create, the next vectors that we are going to create will only consider the frequency of the words and not their order. Now, if we do that, we only have to uh, basically, if we do that, if we are presented only one sentence and we have all the words in it, we simply add one for every word. And if in the representation bag of words representation for that sentence would have all ones. But if we have more than one sentence, like this one over here, let's say we have a couple of words here. Thomas Jefferson listing 2.7. 1 second. I open the listing 2.7, 2.5, 2.7. So this is the first sentence as we were seeing 2.4. Okay. So I'd explain. This is the first sentence. Thomas Jefferson began building Monticello at the age of 26. What is the second sentence? Construction was done mostly by local masons and carpenters. So this is the second sentence. Third is he moved to the South Pavilion in 1770. And last is turning Monticello into a neoclassical masterpiece was Jefferson's obsession. Now, if we look at it, like we noticed earlier, numbers come first, right? And so what numbers do we have over here? We have 26 and 1770. And if we start building bag of words for them, we would see that 26 is 1 for sentence 0, but 1770 is 0. 2026 is 1 for first sentence, and 1770 for first sentence is 0, because 1770 is not here. And how we got this for this x-axis, how did you build this vocabulary is by parsing. So what happens, you tokenize, you pick every word in it. Thomas is there, Jefferson is there, began is there, building is there, Monticello at the age is there, of is there, 26 is there. Tokenization gives you the words, you sort them, you put them in order. 1770, 26, construction. So I'd write it down, 1770, 26, construction. Can you tell me which is going to be the next word? Some word with capital letter. I think it's gonna be Jefferson. JKLM. Yeah, it's gonna be Jefferson. EFGH. I think it's gonna be he. So this is sort of how the vectors are built, and we can take down the last from here. Pavilion South Thomas. I think he has this author has only picked out the capital words and not the um, not the small words.
Hmm.
So twin building the vocabulary. Now once we are doing that, uh, we have to construct a matrix of this form, zeros and ones. So for every word in that sentence, we put a one for the column corresponding to that word. So this gives you the one hot vector. No, no, this bag of words model for your bag of words vector for your sentences. And this is basically just for additional information. Dot product is a very important operation in NLP. This is one of the matrix operations that I found in one of the pages in the book, and you can just remember that algebraic definition of this is if you're given a dot p and you know the values a1 b1 a2 b2, it's sort of like this: a1 b1 c1. One second, some issue. Okay, a1 a2 a3, a1 a2 a3, b1 b2 b3. Then you multiply them. This is the dot product of these two vectors. Then what is the geometric definition? Geometric definition is simply a dot p, meaning mod of a mod of b and cos theta. Cos theta is anti clockwise direction. You take theta angle is taken in anti-clockwise direction. Now if you have, this is for understanding that if you want to find out the number of common words which is present over here, overlap of word counts for two bag of words vectors. So if you do it, shall we do it as an example? Let's do it as an example. Over here we would take two vectors, text box and send 0 equals to I am Ashish, and send 1 equals to maybe not. So how many? So we would not sort them. We would simply um, use them as is. I am. Do you understand, or shall I need to explain this?
It's fine, Ashish. I mean, I'll be able to understand.
Okay, just a second then. Sentence 0. I am Ashish, maybe I'm not. I is there in sentence 0. So 1, 0, am is there, Ashish is there, maybe is not there, and not is not there. Sent 1. Then I is not there, am is there, Ashish is not there, maybe is there, and not is there. Now when we dot product the two, uh, sent 0 dot sent 1, the vectors, as per the definition of vectors, we have to multiply this number by this number. So 1 times 0 plus 1 times 1 plus 1 times 0 plus 0 times 1 plus 0 times 1. Now this gives you essentially 1 because there are zeros in rest of the figures when 1 times 1 is 1. So number of common words in these two sentences is 1. These two sentences is 1. An application of dot product. Now, if we go to the next slide, several Python packages, we are coming to the application point of view, like what do we have? We have several Python packages implement tokenizers, each with its own advantages. You must have heard of Spacey, NLTK, and Stanford Core NLP. Spacey is the industry standard for doing basic tasks such as tokenization, but otherwise NLP is also a very good package. Stanford Core NLP, I have personally not used this as it uses Java, and most of the work that I have done is in Python. And it's good to remember these two packages for now, as most of our examples are in Python, and this book is also written in Python. Now, Tree Bank Word Tokenizer. This is a tokenizer that's available in the NLTK package, and this is a piece of code that is explaining you how to use it. Well, you do the import, you create an input sentence, you initialize the tokenizer variable by calling the constructor for that tree bank word tokenizer class, and then you use the tokenize method of tokenizer to tokenize a sentence. Now, as you can see, this tree bank tokenizer has been trained to understand contractions as well. What are contractions? The words such as wasn't, don't, there as in they, THEY apostrophe RE, it's able to understand them and break them into separate words, such as if we have a sentence, Monticello wasn't designed as UNESCO World Heritage Site until 1987. This word wasn't has been broken into two, was and not. Not exactly not, but N apostrophe T. So tree bank word tokenizer is a pretty good one. You can use it in your projects. Stop words. What are stop words? These words are basically which are extensively used in your English language writing, and you can safely ignore them for your NLP application. Now, at times it is not advised that you remove stop words such as the word not, because it changes the meaning of the sentence, such as in the problem of sentiment analysis. What happens is that if you tell the sentiment analyzer I am happy, and you use the stop words removal to remove I am, then only happy is left. Happy is passed to the sentiment analyzer. It reads happy and says that the sentiment is positive. Now, if you have stop word removal library, which is also going to remove the words such as not, then that will create a problem, because if you using stop words removal and the input sentences, I am not happy, stop words removal will remove I am not, and only happy will be left, which will result in the wrong output of positive sentiment. So at times stop words removal is not a good idea, because these stop words help us figure out the relationship between the words, what relationship is present between different relation, what relationship is present between two words, such as the example shown over here is Mark reported to the CEO and Susan reported as a CEO. Just a change of single word of to as, which both of which are stop words. You are essentially destroying the meaning of relation, the all the context of relationship that Mark and Susan have with the office person CEO. Now, Susan is the CEO, Mark is the reportee, but if you remove the stop words, it both becomes Mark reported the CEO, sort of the will also be removed, Mark reported CEO, and for Susan, it will be Susan reported CEO. So this is kind of becoming we are losing the relational information in the text by removing the stop words. Now, next is word embeddings. Now, word embeddings, document parsing ends here and word embeddings begin. We don't have too much content for word embeddings right now, but all that you need to understand is that computers work with numbers at the most basic level. They work with zeros and ones, and to make your text understandable to a computer, you have to turn it into some kind of numbers, and those numbers are called word embeddings. Now, there are some word embeddings which are local, some are global, but one second, if we have that here, I would not. Okay, so when we talk of local word embeddings, what we saw over here, like over here, if we have some kind of text, the embedding for the Jefferson is 0, 1 and all zeros in the one hot vector representation. The embedding for the word, one second, I is, I think this is a bit this is a bit confusing, because I would need to figure out how the word embeddings concept comes here, but basically it is the representation of the document and not the words. But when we do something like this, we are essentially converting our corpus, our input, into numbers that are understandable to the documents. And we have the concept of local word embeddings and global word embeddings. Now, when we talk of local word embeddings, they are created by count vectors such as this count, one second, um, count vectors, number of times it appears in the document, uh, count vectorizer. So there is a concept called count vectorization, which should be able to return the word local word embedding for these words with respect to sentence 0 and sentence 1. But we also have a concept called global word embeddings, which essentially take the name of glove or word to vec or word embeddings. But to begin with, to conclude this session on one line, global word embeddings are fixed length embeddings that know what a word is, and they understand the word in terms of its features, such as its gender. What is the gender of the word, animalness of the word, peopleness of the word, if the word is the name of a place or a thing, or even if it is a concept. For example, if a word embedding bird understands, whether if bird understands, if you uh, talk to it, talk to it about Python, bird would understand whether you were talking about a reptile, talking about a reptile or not a reptile, but let's the animal, the snake, the snake, or the programming language. So concept is also captured by global word embedding. So this was all for today. Thank you for joining. Any questions? Any questions? You have any questions, Kanika?
No question as such, but there was a term in one of the slides, engram. Yeah.
Okay, and yeah, this one I think. Okay, engrams. So when we call engram, it is, we basically mean 2 gram or 3 gram or 4 gram, and mm, or and so on and so forth, so on. right? In 2-gram meaning, we have to take out words together. Like if we have this sentence, and we will copy it here. When we have a tokenizer that is picking out, it will pick out Thomas Jefferson. Jefferson began building, and so on. And when we talk of 3 gram, it will be Thomas Jefferson began Jefferson began building, and so on. So by 2 grams and 3 gram, we basically mean how many words do we want to take together to form a token. A 2-gram token means there are going to be 2 words in it. A 3-gram token means that there are going to be 3 words in it. Clear?
Okay. Yes.
Any other query, or we can close?
Yeah, we can.
Okay, all right. So Kanika,